Okay, good afternoon now. It's my pleasure to introduce Dr. Yakov Pachepsky. Dr. Pachepsky actually was born and raised in Ukraine, and he got all his education in Russia. So he got his bachelor's, master's, and PhD at Moscow State University, which is considered the premier university in Russia. And then in 1987, he received an additional honor. In the European system, you can become a doctor of science once you become very distinguished. So in 1987, he was awarded the Doctor of Science award. He has worked at USDA-ARS for about 25 to 30 years. He joined the staff there in about a little over 23 years ago. In 2019, he's a senior research scientist with him. In 2019, he was awarded the super grade rank, which is the top 0.2% of all scientists within ARS. He's a fellow of, SSA, ASA, American Association for the Advancement of Science. He's won several different awards. He's been Senior Research Scientist of the Year before. He's also sat on the U.S. National Academy's Committee for Soil Science. He's published in his career 553 publications. Of those, 358 have been peer-reviewed, and those are the English ones, not the ones in Russian. His Scopus score is over 12,000 citations, not counting in Russian. And in Google Scholar, it's 46,000, over 46,000 citations. And so he's going to talk to us today. And so his training is in soil science and applied mathematics. So he's promised there'll be very little math today. Okay, this is a talk he gave 2 weeks ago to the ARS National Committee on Artificial Intelligence. Okay, so he's going to give the same talk he gave today. Thank you, Yakov.
Thank you, Bob. Thanks for coming. Let's go for this one. So it's a long title. It's 25 years of using machine learning for the development of Pedotransfer functions in soil hydrology. And there is a disclaimer to make here. There's only one equation and no computer code. So if you come for that, don't expect. So what is Pedotransfer really? So we have this distinguished group of people who are called soil scientists, and they, of course, doing pits, describe what they see, take samples, measure properties of soil, and so on and so forth. There is another distinguished group of people who are hydrologic modelers, and they would run the models to estimate flow of water, contaminant transfer, so on and so forth. These two groups should be as yin and yang, but they are not. And so the Pedotransfer research is really a way to try to decrease the gap between these two groups. So what model needs? They need parameters that describe the ability of soils to conduct water and to store water. And measurements of these parameters are possible, but they're extremely time-consuming, labor-consuming, whatever consuming is. So if you have a project with a high area, you just can't take samples in these amounts. So the idea is this Pedotransfer activity is to convert data we have from the soil survey, from soil analysis, limited number of soil analysis, into the data we need for these hydrological models. And essentially what it is, it's you use data on soil composition, you can use data on landscape situation and land use. And what you want water holding capacity, you want to know how the soil conducts water, sometimes other things like bulk density and so on. That's what Pedotransfer is. Pedotransfer is actually fairly healthy research field. And the reason for that is that it has multiple users. Has users in all the list of these disciplines, and that's not complete list, really. If you look at the bibliometry, at the right side of this slide, you have a graph of the dependence of the number of Pedotransfer papers per year depending on the year. And it's steady growth. You may call it exponential if you're patriot of this one, or just growth. One thing I need to say that it's probably underestimation, because the word Pedotransfer has synonyms, and sometimes people do the same thing but just don't use the same word. So probably 2 or maybe 3 times more. And the first book on the Pedotransfer, which was published in 2004, it's shown in the left corner. It had, I think, 11 editions already. So it's healthy field. Now, it's a little bit inconvenient to see this. But you can see it either. You can see the top of the slide. For this slide, the top is the title of the slide is. Thank you. So why machine learning? Why we came to this? This is the example of just a piece of Excel table. And the first column contains water holding capacity. The first column, this one. And all other columns, beginning from B to the end, they contain soil properties that may be used as a predictors of field capacity. They're all potential predictors. And what's our problem here? First, there are many of them. So we don't know which one to take, or take all of them, or how do you do this? Second question is that we don't have equation which would connect these properties to our target variable, which is water holding capacity. We just don't know what equation to use. The third issue is that we expect that this relationship is very complex. It shouldn't be very simple. Otherwise, it will be known already, right? And next thing is that, which is important, in different parts of the database, you can have different relationships, different type of relationships between the target variable and predictors. For example, if you have, let's say, look at the water holding capacity, and you look at organic matter as a factor, and you go to sandy soil, you will have one effect. You go to the clay soils, will have different. So in this situation, the regular statistics cannot help. There's no techniques. And machine learning can. There are many definitions of machine learning, because it's a burgeoning field, and everybody comes with his or her own definition. What we're going to do here, we use the operational definition, which is written at the bottom of this slide. And what it is, it's the computer algorithms that do the predictions, classifications, or optimizations with a large number of input variables. That's the key here. So what do you do if you have a large number of potential predictors? So a little bit about timeline milestones, how the whole thing developed. About 350 years ago, there was a famous French playwright, name was Molière. And he wrote this story, which is no play really, which is the bourgeois gentilhomme. And the hero of this story, Monsieur Jourdain, he was very surprised when he learned that he was speaking prose all his life without knowing this. Pretty much same thing happened to us. We were developing Pedotransfer functions using machine learning without knowing it, beginning from 1995 to, I guess, 2014. So that's a timeline here. The two portraits are the guys from ARS who started the whole thing, being this staff scientists. Dr. Walter Rawls, he was in hydrology lab. Dennis Timlin, now in adaptive system, crop systems lab. So this very, very brief titles basically show how the whole thing developed. Started from the neural nets, and then there was this, let me see, what was it? Database dependence was very important, that results really can easily transfer from one database to another. Then there was group method of data handling was introduced. What's very important realization that was uncertainty in results of this Pedotransfer. So machine learning it wasn't realized immediately. That uncertainty is important. Then the regression trees were introduced, very powerful algorithm. Then several other powerful algorithms, and then in 2014 it was explosion machine learning and a bunch of various algorithms. Now probably more than 200 are known. This one note here is that all this work was done practically with the participation of foreign scientists. So this one was Hungarian group, and this one was Dutch, and this one was New Zealand. This one was again Dutch. Oh, this one didn't have anybody. This one was with Polish. This one, and so on and so forth. So it was an international effort, actually. That's what I'm trying to say. Although ARS was an important player in this development. So what were the purposes? So what people wanted to do when they were applying machine learning. One thing, of course, which is the left side, it's improving Pedotransfer skill. And what skill is basically performance in three fields: accuracy, reliability, and utility. Accuracy is the performance of the model, the data it sees when it is trained. Reliability, it's performance of the model on the data which it did not see, right? It's when it is tested. And utility is when this thing is not tested per se, but it's inserted into big hydrological model. And then the question is how the big model performs after this insertion. There's two things to note here. One of them is that all metrics should be treated as a random variables, which is important, because essentially what it is, you compute R squares and you're happy with this. But in fact, with machine learning, there is no single R square. R square has a distribution, it has the spread, it has the mean, and so on and so forth. So, and that's how it has to be treated. Second is the skill may not matter in some cases. So we may strive to find a very accurate Pedotransfer function, but when you stick it in the hydrological model, no difference. So it is important. So you need to really know what accuracy you want. But then it was realized that there is another result that can be obtained with using this machine learning. And this is the finding influential predictors. And it's obviously important because if there are influential predictors, this is what you have to measure. That's what you have to learn about. Eventually it was found it's just a sensitivity issue, but also sensitivity to missing data. And the missing data is a common menace in soil database, not only soil database, any big database. And so how deal with this, it became an issue. So what's special about machine learning? Let's look at this thing. Very important thing is that there is a very strong connection between machine learning and biological or sociological observations. It's really underpins the whole machine learning story. So machine learning methods, they either fully or partly rely on the hypotheses which are coming from observations made in biology and sociology. It's not mathematical, purely mathematical method. Techniques are mathematical, but they're underneath, no. Now let me show you one example here. One example, what they call genetic algorithms. So say we have a mathematical model, which already we know, and we know the parameters of this model, the P1, P2, Pn. What we want to do, we want to find values of these parameters. After using which we will have a good fit. It's a very common operation in mathematical model. So we know that in the computers, numbers are represented with zeros and ones. That's a binary representation. So what we're going to do, we're going to build a string here. So this part of the string is a binary representation of the first parameter, this one, the second parameter, and so on and so forth. And then we claim that this string is a chromosome. So we generate randomly several of these chromosomes and say, okay, they're our parents. And we want to find their descendants. So we generate a bunch of descendants, and we pick up those who are more fit. Give you a better performance of this model we started. And then we make a next generation of these fittest guys, and we make next generation, so on and so forth. It appears that we need to introduce mutations, otherwise the process is getting stuck. And what happens that, first of all, there is no mathematical proof by any means that this process in fact will work. Second is the empirical evidence that this process works beautifully, much better than the processes that actually have underpinning mathematical basis. If you look at this table, at the left side, we have the names of the algorithms, so machine learning algorithms, which belong to so-called classic machine learning, because there is now advances called the deep learning. We'll talk about. And at the right side is the biological hypothesis or theory, which was actually sitting beneath this approach. For example, the genetic algorithms, we saw how it works. It's just the survival of fittest. Now there's a group method of data handling or random forest. This thing is based on the sociological observation of wisdom of crowds, that the group of people may come with the reasonable answer to the problem much better than the individual experts. Classification regression trees, that comes from the sociological recommendation. If you want to study something heterogeneous group of people, then you need to find and study the very homogeneous inside and very dissimilar from each other groups of people. So that's a standard trick of sociology. Support vector machines, this is another algorithm. The basis here is that animals and humans are essential coarse resolution. When we reach our goals, we don't pay attention to the small errors and small mistakes. And that's how this algorithm works. Of course, artificial neural nets is the neuron activities in the brain. And the nearest neighbor, the similar predictors, lead to the similar target variables. Now, there is no guarantee that any of these concepts will be applicable to your data sets. So you have your database, and which one will work, or no one can tell. The simple example is, let's say you look at this nearest neighbor. It's kind of trivial. Yeah, the closer are predictors, the closer is your prediction. Yes, if you have all important predictors. But if you don't have them, important predictors, then what may happen in the realm of the predictors that you have, they will be close. Your two objects will be close. But in fact, with these important predictors, they're very far from each other. And pretty much happens to all of these hypotheses. There's no proof. Another thing is the machine learning and scale. That's an interesting question. Well, we know that the soils are studied at different scales. You can study at kind of centimeter scale, look at the arrangement of particles, the property of the surface, and make some conclusions about how this soil will retain water, or it will conduct water. Well, you can go to the next scale. If you will profile, you will see this macropores coming from the soil animals or from the root canals and so on, and see how these things would affect your flow and transport. You can go to the next scale and to see how the flow is partitioned to the lateral and vertical. You can go to the next scale to see how the soil associations allow you your material to move to the streams, and water moves to the streams. What is important that the regular statistics, traditional statistics, relates variables obtained at the same scale. So essentially what you do, you take sample, and then you can measure various things in this sample, and then you try to relate these things to each other. Machine learning appeared to be efficient when you use variables or values coming from different scales. And the example of the next slide will be on this for the soils with moderate and large extent in the United States. Okay, this thing is a decision tree, or actually a regression tree. So this value is at the bottom, the second one, that's our target variable. This is our water holding capacity, or no, it's not water holding capacity. It's really the amount of water in that soil is able to hold at minus 33 kilopascal. So the samples in which this amount is measured are very small. That's what it is. But then, how to read this thing? If the soil is more or less sandy, has a lot of sand, then you need to go this way. And if your slope is less than 8.5, you go this way, and otherwise you go this way. If you are in these horizons, okay, then you go this way, and you are in other horizons, you go this way. So let's say if we move along one of these trajectories, we're coming here, what it basically tells us that the water holding capacity will be very small in the soils with the low slope value, and in the horizons T, B, C, B, and generally B horizon. So if you move other things, you go to the clayish soil, the content of clay is high enough, and you are in these horizons, then you go this way, and then you go this way. And if you are on other horizons, you go this way. In each of these cases, you are getting a value, and this value is fairly good representation of what happens. In spite of the fact that almost everything here is categorical, it's not numbers. It's just a class, really. Textural class, horizon, position at the slope. You still have accuracy R squared about 0.8, which is very high. And second thing, which is probably important, I talked about it, that you don't need to have numbers to use machine learning. You can be very well off using the categories. And that's important because then you can use maps. Because on the maps, you have something categorical. You don't have numbers on the maps. Next thing, question is, how many data sets does one need to apply machine learning? There is no clear recommendation, frankly. It depends, nobody can tell you. It depends on the machine learning algorithm that you're going to use. And also it depends on what do you want from machine learning. For example, if you want to use decision trees and just to see the structure of your database, what variables are best in splitting database into homogeneous pieces, which may be all you want, then it's 10 to 2. So if you are within 100 samples, you can be well off. However, if you're going to use deep learning, that's the machine learning methods which are used in text recognition, speech recognition, image analysis, and so on, then you need a lot of data. 10 to 5 data sets, that's what you need. So it's really, generally speaking, if you want to know the predictor influence, then you may be well off with a small number of data. So it's not critical to have large number of points. Next question is, okay, if this is the case and we are somehow dependent on the volume of database, then question is, if I will increase database, will I be better off? Sometimes you can do it, increase database. So hopefully yes, but in fact, as you increase the database, you typically encounter heterogeneity within this database. You're not sure what to do with it. For example, example number one, measurement method. There are about, 12 or 13 methods to measure soil hydraulic conductivity. And if you in the same database, you have these values are measured with different methods, then you don't know what to do with it, because the different methods will give you the different results at the same soil. Next thing is regional classifications. It's a legacy issue because before American classification conquered the world, soil classification conquered the world, countries were developing their own classifications, and sometimes they stick with them and they have databases built in this thing. And how to go from one classification to another, people are working on this one. Cluster data, it's very common. Let's say you measure the same thing in two different locations quite far from each other. Then if you combine them, there are some conditions that you don't account for, of course, when you combine them. And then you have two different groups. And the resultant application of machine learning will not be good of any of them, any of them. Missing data. Missing data is a menace, as I mentioned, and there are methods of what they call imputation, sticking something which may be looking like truth. But all of these methods are iffy, unfortunately. We tried many of them and didn't work. Then the cleaning of databases, sure thing, needs the cleaning. And then the question comes, what to do with the outliers? Because outlier may represent something very real. We just don't have enough representation of this real thing. For example, if you look at American databases, soil databases, you will try to find silt soils, so you can find them. There are some samples coming from southern Appalachia, but realistically, no. So when you're having something like that, is it underrepresented or it's really trash and you need to get rid of it? It is not clear. And the final thing is weak representation of degraded soils. Typically, we have much less data on this type of this situation of degradation, but that's when we need these pedotransfer most, because what we are interested in the global change and all these important things, but essentially at the end of the day, we will be interested in degradation. There are methods now, fortunately, that when we can get a lot of soil data. The left side, it's looking this one. It's not a mahjong. It is a consecutive maps of soil electrical conductivity. It's one of the students of NST was measuring in Beltsville Agricultural Research Center. Zain Hadzik was name. You have quite a bit of data here. So you can apply complex machine learning methods and really build something predictive. Another way to get a large number of data is, of course, to just set a bunch of measuring devices and measure, let's say, water contents and temperature. We did it for the US Nuclear Regulatory Commission. And this way you can get 2 million numbers for a year. It's a lot of numbers to use machine learning. You can use drones and drone imagery and use some kind of indices which show the plant state. And then the Charlie Walcall in the beginning of 2000, he suggested that, oh, guys, if you can do that, then you can build a map of the ability of soil to retain water, because that's what controlled the state of plants in this situation. Finally, you can go ahead with what they call proximal sensing and use the spectral characteristics of the soil properties of surfaces, particles, and then you trade quantity for quality for quantity, or quantity for quality, and you can make some conclusions about the soil properties. So there are ways to get a lot of soil data, and it basically expands the applicability of machine learning. This is a little bit of dialectics here, exploratory and confirmatory. Unlike the classical statistics, machine learning is conceptually exploratory because there is no hypothesis to confirm. See? And if you have a machine learning algorithm, you always have the knobs to turn. It's called hyperparameters. And if you do this, if you turn these knobs, then you can change the skill of the predictive machine learning model, sometimes drastically. So we saw increasing R squared 2 times, which is just almost impossible. So the performance results are data-driven, but this tuning may help to do what? First of all, to find hidden relationships in your database. You don't see it, we don't know that. And even the correlations will help you, but they are there and you can find them. Another thing, the data suitability. So you can find a set of data which are just no good. Internal structural database, it's important to know what are the homogeneous pieces in your database. And also the uncertainty in skill improvement, it's also comes from database. So it is not, it's not statistics really in complete sense of it. Another question is delivery. So the machine learning is full of mumbo jumbo. You just read it. You need to have a patience to understand what they do. Now, let's suppose you applied machine learning in your work, and you want to publish or report it somehow. To do that, you may go in 3 ways. Way number 1 is this: you have to be brief, and you can say, okay, well, we applied the X method, which was known to show good results in this work Y, and it gave good results to the Z type of database, data sets, so we are using it, possibly. Another way you can go further, and you can build a diagrams. For example, this is a diagram how the information goes into the neural net. So from this input to all these neurons, and then goes. It's not a complete description because it doesn't tell you really what's going on with the information. You see where it goes, but you don't know what happens to it. Then you can write an equation. I promised one equation. That's one equation. This equation actually works. It explains how the neural net works. And then if a mathematician will come here, he will tell you, oh, guys, this is the continual fractions, and continual fractions known to be a very good approximators. You can fit anything. Now, you can tell what will happen in the journal when you send your paper with any of these things. At this point, it's still new. There is no policy. And some journals don't want to publish machine learning at all. I can see it. Some journals are very eager to publish it, but they would require one of these types of representations. So you need to be careful if you're trying to publish, you may expect some kind of hiccups. And the second question here is usability. If you want to use this thing, then how? There is this program, Rosetta, which is extremely widely used in the world. It's a lot of references, even more without any reference. It's a neural net which predicts soil water retention from soil composition and some other parameters. So why it's widely used? It's widely used because it is implemented as a code. You can get it, you put stuff in, you go. But it's not that way in the with the majority of machine learning products. So this is the list of names for the machine learning algorithms. It's about 1/3 of them, of names. When you just say that, okay, you apply this one and you got a good results, what does it mean for a reader? Nothing. Reader would like to use it, but how? When you report what you did, there is no protocol of reporting. And it creates a little bit of problem. I guess this machine learning community has to think how to really make it available, make results available. The last thing is this sorcerer apprenticeship. That's actually came from my friend of mine, the Dutch scientist Johan Boma, and I asked him, okay, why he came up with the word Pedotransfer to begin with. So I asked him, why did you introduce such an ugly word? And he says, because that's what people will remember. So, but this is a story of the poem of Goethe that, yeah, you start something, but then you don't know how to stop it. So, nevertheless, of course, machine learning has limitations and uncertainties, and some of them are listed here. So one of them is there's no significance level. It creates a problem because we are accustomed to have some kind of probability of. Second, evaluation of information content in dense inputs. I don't think there is a clear approach to this one. Consider the spectrum, okay? And if you consider the two signals at the two neighboring wavelengths, of course they will be correlated. Then the question is how far you need to go in the spectrum to get something meaningless inputs. It requires work. Usually people don't look at the uncertainty in predictors values, not in the results, but your inputs. But actually they are random variables as everything in the world. And that needs to be researched. The obvious weakness of machine learning is that there is no physics, chemistry, biology, or anything constraints in the procedures. And that's not good. People know that, people are trying to do something about it, but so far it's very empirical. So it's two different worlds, data-driven model or mechanistic driven, they separate. People are trying to get them together. Region for database specificity, yeah, we talked about this. It's maybe an issue. And classical statistical methods, if they're applicable, they're better. They give you much more information than machine learning, because machine learning is always a little bit of black box. I'm going to skip this one. And the last three slides are coming from the Matt Stoker, who was supposed to give this talk. I'm really feeling for him. And he's just got sick. And I asked him to give me the resource slides. What are resources? What he thinks are resources. First slide is, okay, what's available here in the University of Maryland? You can see that there are several courses with different prerequisites. Some of them don't require prerequisites, some of them require easy prerequisites, some of them are hard prerequisites. So there's a range of things you can do here on campus. Second slide is the code. So how available, you need the code to apply machine learning. And nowadays, there are several types of code which are available in Python, in R. There are separate packages which really don't require any programming. So it's a variety of things. So you are not on your own when you begin to do this. There are many things you can take from the shelf and start to apply. And finally, what the publications are out there. So that's a good one, really. This is a brilliant one. Because it's very short, it's 100 pages, and it has a very good content. One. So thank you for your attention. Happy machine learning. And next thing would be, or should be, it's machine learning and artificial intelligence, because the machine learning is a part of artificial intelligence. Thank you.
From the audience? Oh, that's the question.
Oh.
Probability distribution models have been around quite a while, and people describe them as black box models because their predictions are only good in the confines of the data set they've been used for. How does that apply to machine learning also? Can you transport those to other systems and look at? I didn't mean to give you a real hard question.
It is the black box also, but see, the black boxes are not the same, they're different. With the probability distribution model, it is data-driven. You're describing only what you have in your database. What you cannot do, you cannot tell which parameters or input variables are important. That you can do with the probability model, but you can do it with some of those. You can ask the question, okay, which variables would give you largest error if I removed? You can do it with the probability model, you can do it this one. So the probability model, to some extent, belong to the same class of data-driven models. Yes.
Yakov, good to see you. Great
Good to see you, Adele.
presentation. As always, I learn from your presentations. Thank you.
Thank you.
You know, one of the things that's mentioned at the end, machine learning, artificial intelligence, and as you know, the use cases to which we apply, whether it is the soil systems or agricultural system as a whole, for water resource management and so on and so forth. So the linkage, the communication that needs to take place between the use areas or those who are experts in use, let's say we are hydrologists or scientists or engineers, how do we communicate with foundational AI builders, which generally are computer scientists, as you know, generally, that doesn't mean that other field experts are not developing it. But how do you see that interface to come together? Because if that's not the case, they're saying that foundational AI people, they can develop algorithms, but if they are not informed by use-inspired areas, they may not be developing right algorithms, and vice versa. Use-inspired people, they need to know what are the limitations and so on. Any comments?
Well, first of all, it's a very big question, and I don't think I can only scratch the surface. What realistically happens? AI is something to make decisions and implement them. To make informed decisions, use machine learning. So everything starts from the task. So you drive a car, right? And you want something which would allow your car to cross the white line, or at least it will begin to beep. So how do you do this? So there are several sensors which are looking at this thing. So that's the situation for machine learning. And machine learning will tell you, okay, this is a dangerous field. Then the AI people come. They need to make a decision. What to do with this information. If they will tell it, okay, the swerve from the white, it will be the expert. So then they begin to develop means to implement the reasonable decision based on this information. Reasonable decision will just get slowly from this one, don't jump to the next lane again. So that's what AI people are supposed to do. So part of AI people, they provide this information to their machinery users. Right? Another part of the AI people, they actually use this information to make this machine palatable. So that's how it works.
For the knowledge. Thank you.
think we have enough time maybe for one more quick question from the audience or on Zoom, perhaps.
Yeah, I need to go. Check.
Probably wrap up this.
Right, well, thank you very much, Yakov. Sure appreciate your coming in today, and you stretched my mind a little bit, I'll tell you. Thanks very much.
Thank you.
Oh, that's really nice.
Thank you.
Thank you very much.